we've just spent 3 videos going through reaction of carbonyl derivatives with hydride reducing agents. The subject of this video will be reaction of the carboxylic acid derivatives with organometallics. So we would expect them to be nucleophilic acyl addition or nucleophilic acyl substitution reactions. When we're talking about organometallic reagents, we're talking about alkyl lithiums or aryl lithiums, like for example, N-butyllithium. We're talking about alkyl magnesium bromides or aryl magnesium bromides. Sometimes iodides. Like the familiar phenylmagnesium bromide that we used in the first lab of this semester. And we're talking about cuprates. Lithium dialkyl cuprates. Lithium dimethyl cuprate. And we know that the cuprate is the least reactive and the softest of the bases. And we know that the lithium reagents are the most reactive and the hardest. And that was made manifest by the fact that the cuprates do exclusively 1,4 addition, the alkyl lithiums do exclusively 1,2 addition, and the alkyl magnesium bromide do a mixture of 1,2 and 1,4 addition to the alpha beta unsaturated carbonyl compounds that we made by aldol condensation. So what happens when we react these various reagents with a carboxylic acid derivative? Like an acid chloride, propanosyl chloride, for example. One would expect that the alkyl lithium or alkyl magnesium bromide would be readily attacked, form a new CC bond. Exactly what we would expect to happen to an aldehyde or a ketone to generate an alcohol, but in this case we have a leaving group, so we can take out the leaving group and complete a nucleophilic acyl substitution. Generate a ketone. However, the ketone is still reactive. Because we already know that we can convert ketones into tertiary alcohols by reacting with organometallics. So we are now going to do a nucleophilic acyl addition to generate an alkoxide salt. by a nucleophilic acyl addition. And that's pretty much identical to what happened with lithium aluminum hydride reacting with an acid chloride, where the first hydride did a nucleophilic acyl substitution reaction, taking out chloride helium group, and then the second hydride reacted with the aldehyde, forming the primary alcohol. You're limited because the ketone reacts with the excess alkyl lithium or alkyl magnesium bromide. You're limited to symmetrical tertiary alcohols, where two of those R groups are going to be identical. An identical reaction can occur with esters and either alkyl lithiums or alkyl magnesium bromides. Hydride reductions. Nucleophilic attack. Loss of the leading group. And then proton transfer from this acid cuprate. To once again generate a tertiary alcohol. So both esters and acid chlorides will react through 4 steps. First, a nucleophilic acyl substitution with the loss of either chloride or the alkoxide as a leading group, followed by a standard nucleophilic acyl addition to the resulting ketone. In this case, it's impossible to stop at the ketone stage because the ketone is in fact more reactive than the ester. Because we don't have the resonance contribution from the oxygen lone pair that reduces the reactivity of the ester. In the case of the acid chloride, though, the ketone is actually less reactive than the acid chloride. So it's theoretically possible to stop at the ketone if we have an organometallic reagent that isn't good enough to do this second nucleophilic attack, that will react with the more reactive acid chloride, but not react with the less reactive ketone. And if you guessed that the cuprate is the reagent that will do that, you are correct, right? We know that cuprates don't add 1,2 to a carbonyl of an alpha beta unsaturated carbonyl. We know that they prefer to add to the 4 position, to the carbon at the end of that alpha beta unsaturated system. So cuprates are good enough the isomer group chloride. Generate ketone. But then the ketone does not react further with the cuprate. So we can stop at the ketone stage. So both acid chlorides and esters will generate tertiary alcohols and symmetrical tertiary alcohols with the more reactive alkyl lithium or alkyl magnesium bromides. Acid chlorides, and only acid chlorides, not the other acid derivatives, can be used to synthesize ketones through reaction with the less reactive organometallic, the cuprate. And it turns out that you can also make ketones from nitriles through reaction with Grignard reagents. Butane nitrile and reacted it with phenyl magnesium bromide. The nucleophilic carbon will attack the magnesium bromide salt, but this negatively charged intermediate will not react with further. Bromide. Means that when we do aqueous acid workup, we can generate imine that imine can be hydrolyzed in 6 additional steps. To carbonyl compound. So again, it's not in this case because the ketone is less reactive than the nitrile. It's because the negatively charged intermediate is the terminal step of the reaction of the organometallic, and then aqueous acid protonates that and then hydrolyzes it to the ketone. So the overall reaction would look like this. Step 1, treat this with phenyl magnesium bromide. solvent. Step 2, we treat it with nitric acid. And that reaction is to generate a ketone from the nitrile. So we can generate ketones from acid chlorides by reaction with cuprates, or from nitriles by reaction with alkyl magnesium bromides. And we can generate tertiary alcohols by the reaction of acid chlorides or esters with alkyl lithiums or alkyl magnesium bromide reagents. And that finishes the summary of the reductions with hydride reducing agents and the organometallic reagents with acid derivatives. Those reactions are summarized. There's a section under potentially useful information on Blackboard that has all of the reactions with hydride reducing agents and organometallics written out for you.